How can we extract minerals from seawater for solar and green manufacturing? Extracting minerals from seawater is a promising pathway for sourcing critical raw materials used in solar energy systems and green manufacturing, particularly as terrestrial sources become more constrained or environmentally damaging to mine. Here's an overview of how this can be done, along with the technologies, benefits, and challenges. Minerals in seawater, relevant to green tech. Seawater contains trace amounts of many minerals useful in green technologies. Minerals and the uses in green tech. Lithium, batteries, EVs, solar storage. Magnesium, lightweight alloys for solar panel frames, EV parts. Uranium, nuclear energy, not solar, but still low carbon. Potassium, boron, bromine. Electronics, photovoltaics. Cobalt, nickel, rare earths. Batteries, magnets, wind turbines. Main extraction methods. Adsorption. Uses specialized materials like manganese oxide or metal organic frameworks that attract and hold metal ions. Most promising for lithium and uranium. Can be deployed in mesh nets or fabrics immersed in seawater. Membrane desalination byproducts. Reverse osmosis desalination concentrates minerals in the brine waste stream. Brine can be further processed to extract valuable elements. This turns a waste problem into a resource. Electrodialysis. Applies electric fields to separate ions based on charge and mobility. Useful for separating magnesium, lithium, potassium, etc. Biomining with algae or bacteria. Some organisms naturally bioaccumulate trace metals. Can be engineered or cultivated in large-scale systems. Solar evaporation ponds. Uses the sun to evaporate water and concentrate salts. Economical in warm, arid coastal regions. Already used for magnesium, potassium, and lithium extraction in salt lakes. Could be adapted for seawater. Integration with solar/green manufacturing. Co-locating extraction facilities with solar farms or desalination plants allows. Shared infrastructure. Energy-efficient processing using solar thermal or photovoltaic energy. Zero liquid discharge designs that reduce pollution. Circular economy. For example, a solar panel manufacturing site near the coast could use seawater for cooling/desalination. Extract magnesium and lithium for panel frames and storage batteries. Power the whole site with solar energy. Benefits. Abundant resource. The oceans contain billions of tons of many minerals. Reduce geopolitical and environmental risks of traditional mining. Can be powered with renewables, making the supply chain more sustainable. Coastal communities could benefit from decentralized mineral sourcing. Challenges. Low concentrations. Most minerals are present in parts per million or billion, so energy efficiency and selectivity are key. Technology costs. Advanced adsorbents and membranes can be expensive. Environmental impact. Careful design needed to avoid harming marine ecosystems, especially when handling brine. R&D and startups to watch. Lilac Solutions, lithium extraction. Renewable materials, Energy X, battery recycling plus lithium tech. Pacific Northwest National Lab, PNNL, developing new adsorbent materials. Takeda, Japan, uranium from seawater research. Extracting minerals from seawater offers a sustainable and innovative way to support solar energy systems and green manufacturing. As the world transitions to renewable energy and electric mobility, the demand for critical minerals like lithium, magnesium, cobalt, and rare earth elements is increasing. Seawater, which covers more than 70% of the Earth's surface, contains vast amounts of these minerals in low concentrations. Although traditionally overlooked due to the technical difficulty and cost of extraction, recent advances in materials science, clean energy integration, and circular economy principles have made seawater mineral extraction more viable and attractive. Minerals in seawater and their applications. Seawater contains more than 70 elements, many of which are essential for green technologies. For example, lithium is used in lithium-ion batteries for electric vehicles, EVs, and solar energy storage. Magnesium, which is present in seawater in significant quantities, is used in lightweight alloys for EV components and solar panel frames. Uranium, although not part of solar energy systems, is considered a clean energy source when used in nuclear power. Other elements such as potassium, boron, bromine, cobalt, and nickel also play vital roles in electronics, photovoltaics, and energy storage. Methods of mineral extraction from seawater. There are several emerging and established methods for extracting minerals from seawater, each with distinct advantages and limitations. Adsorption. This technique uses specially engineered materials that can selectively attract and bind certain ions from seawater. Adsorbents such as manganese oxide, polymeric resins, and metal organic frameworks have been developed to target elements like lithium and uranium. The adsorbent materials are often shaped into fabrics, meshes, or beads that are immersed in seawater, where they collect trace metals over time. Once saturated, they are removed and processed to recover the metals. Desalination, brine recovery. Desalination plants produce large amounts of brine, a concentrated saltwater byproduct. This brine contains higher concentrations of minerals than seawater, making it an efficient source for extraction. Minerals can be recovered from this brine using precipitation, ion exchange, or solvent extraction techniques. This approach has the added benefit of addressing the environmental issue of brine disposal by turning waste into a resource. Electrodialysis. Electrodialysis uses an electric field to separate dissolved ions through semi-permeable membranes. It is particularly useful for extracting ions such as lithium, potassium, and magnesium. By adjusting the voltage and membrane properties, specific ions can be concentrated and removed from seawater or brine streams. Biomining and bioaccumulation. Some species of algae and bacteria have a natural ability to accumulate metals from their surroundings. These organisms can be cultivated in controlled systems where they selectively absorb trace elements from seawater. After accumulation, the biomass is harvested, and the metals are extracted through chemical or thermal treatment. This method is considered environmentally friendly and is the subject of ongoing research. Solar evaporation ponds. In arid coastal regions, solar evaporation ponds are used to gradually evaporate seawater using sunlight. As the water evaporates, salts and minerals crystallize and can be harvested in stages. This technique is currently used for salt and magnesium production and has the potential to be adapted for other minerals such as lithium. Integrating extraction with solar energy and green manufacturing. To maximize sustainability, seawater mineral extraction can be integrated with solar-powered infrastructure. Co-locating extraction facilities with solar farms or desalination plants creates synergies that reduce energy costs and environmental impacts. For example, solar thermal energy can be used to power evaporation ponds or to provide heat for chemical processing. Photovoltaic systems can supply electricity for electrodialysis and pumping operations. This integration supports the development of a circular economy where renewable energy powers the extraction of materials needed for green technologies. A solar panel manufacturing facility located near the coast could use seawater both for cooling and for mineral extraction. It could recover magnesium and lithium for use in panel frames and storage batteries while using solar power to run the entire operation. Benefits of seawater mineral extraction. There are several advantages to extracting minerals from seawater. Abundant resource. The oceans contain vast quantities of dissolved minerals, offering a virtually inexhaustible supply compared to land-based reserves. Sustainability. Seawater extraction reduces the need for environmentally damaging mining operations and can be powered by renewable energy sources. Geopolitical stability. It offers an alternative to dependence on mineral imports from politically unstable regions. Waste reduction. Utilizing brine from desalination plants can reduce environmental harm while producing valuable byproducts. Challenges and limitations. Despite its promise, seawater mineral extraction faces several challenges. Low concentrations. Most valuable elements are present in extremely low concentrations, parts per million or billion, requiring highly selective and efficient extraction technologies. High energy and material costs. Some advanced adsorbents and membranes are expensive to produce and maintain, and processes can be energy-intensive. Environmental considerations. Extracting and processing brine or returning it to the ocean must be carefully managed to avoid ecological disruption. Scale and infrastructure. To make a meaningful impact, these technologies must be deployed at large scales with sufficient infrastructure and investment. Future outlook and research directions. Ongoing research is focused on developing more cost-effective and efficient adsorbent materials, improving the selectivity of membranes for electrodialysis, and optimizing biomining systems. Several startups and research institutions are exploring scalable solutions, including Lilac Solutions and Energy X, which focus on lithium extraction technologies. Pacific Northwest National Laboratory (PNNL), which is developing new sorbent materials for uranium and lithium. Japanese research efforts, which have demonstrated offshore uranium harvesting using adsorbent nets. As these technologies mature and renewable energy continues to expand, seawater mineral extraction could play a key role in building resilient and sustainable supply chains for green manufacturing and clean energy systems. The energy devices and green technologies that can be made from seawater or minerals extracted from seawater. A wide range of energy devices and green technologies can be manufactured using minerals extracted from seawater. These minerals are essential to modern clean energy systems because they enable lightweight materials, high-performance batteries, solar panels, magnets, and even fuel production. Below is a comprehensive breakdown of what can be made and which seawater-derived elements contribute to each technology. Green technologies and energy devices from seawater minerals. Solar photovoltaic (PV) panels. Key seawater-derived minerals. Magnesium, used in lightweight alloy frames that support solar panels. Boron, a dopant used in silicon wafers to create P-type semiconductors. Silicon, indirectly while not directly extracted from seawater. Silicon processing can benefit from desalination byproducts and chemical inputs derived from seawater. Why it matters. Lightweight frames made from magnesium alloys reduce shipping and installation costs, while boron is critical for semiconductor function in solar cells. Lithium-ion batteries, used in EVs, solar storage, grid backup. Key seawater-derived minerals. Lithium, core component of cathodes and electrolytes. Cobalt and nickel, used in high-capacity cathode materials like NMC, nickel manganese cobalt. Magnesium, experimental, also being studied as a potential replacement or enhancement to lithium in next-gen batteries. Why it matters. Seawater holds trillions of tons of lithium, which is essential for the energy storage revolution. Fuel cells and hydrogen production. Key seawater-derived minerals. Platinum group metals, trace amounts catalysts in proton exchange membranes. Chlorine and sodium from seawater electrolysis, byproducts of water splitting. Electrolysis can also be powered by renewables. Why it matters. Hydrogen production via seawater electrolysis is a pathway to clean fuel, and fuel cells power EVs, ships, and backup systems with water as the only emission. Wind turbines. Key seawater-derived minerals. Rare earth elements, REs, neodymium, dysprosium, and praseodymium are critical for permanent magnets in wind turbine generators. Magnesium and aluminum, used in lightweight structural parts. Why it matters. The generator in a wind turbine relies on powerful, compact magnets made using REs, some of which are found in seawater, albeit in extremely low concentrations. Electric vehicles, EVs. Key seawater-derived minerals. Lithium, cobalt, nickel, used in EV batteries. Magnesium and aluminum, used in lightweight car frames and parts. Rare earth elements, used in electric motor magnets. Why it matters. Reducing vehicle weight increases efficiency and range, while battery chemistry determines cost and performance. Energy-efficient electronics and smart grids. Key seawater-derived minerals. Gallium and indium, trace elements used in high-performance semiconductors and LEDs. Boron, semiconductor dopant. Why it matters. These materials allow efficient power conversion and management in everything from grid-scale solar inverters to LED lighting. Nuclear energy. Key seawater-derived minerals. Uranium, present in seawater at 3.3 ppb, can be harvested using adsorbents. Boron, used as a neutron absorber for controlling nuclear reactions. Why it matters. Uranium from seawater could provide a virtually unlimited source for carbon-free nuclear power, reducing dependence on mined uranium. Green hydrogen and synthetic fuels. Key seawater-derived materials. Water, H2O electrolyzed to produce hydrogen. Magnesium, calcium, could play roles in carbon capture and storage, CCS, or mineralization processes to synthesize green fuels. Why it matters. Hydrogen and synthetic fuels produced from seawater and powered by renewables offer alternatives to fossil fuels in hard-to-decarbonize sectors like aviation and shipping. Why seawater as a source? Seawater is an appealing source for several reasons. It holds vast reserves of critical and strategic minerals. Extraction can be paired with renewable energy systems, especially in coastal or arid regions. It supports the circular, decentralized, and low-impact supply chain for green technology manufacturing. Materials research in progress. Researchers are also investigating magnesium air batteries using seawater magnesium, graphene production from carbon-rich marine biomass, bio-based rare earth extraction using marine bacteria and algae. How does bio-based rare earth extraction work? Bio-based rare earth element (RE) extraction is an emerging field that uses biological organisms, mainly bacteria, algae, and fungi, to recover rare earth elements from seawater, mine waste, or other low-concentration sources. These elements, like neodymium, dysprosium, and lanthanum, are critical for clean technologies including electric motors, wind turbines, solar panels, and high-efficiency electronics. What is bio-based rare earth extraction? Bio-based extraction refers to the use of biological systems or bioengineered processes to capture and recover rare earth metals. These systems exploit the natural affinity of some microorganisms to bind, accumulate, or transform metal ions from their environment. Biosorption. This is a passive process where dead or living biological material, e.g., cell walls of bacteria, algae, or fungi, binds REs from water. How it works? The surfaces of microbial cells are rich in functional groups, e.g., carboxyl, phosphate, hydroxyl, and amine groups. These groups have a natural tendency to attract and bind positively charged metal ions. When seawater or industrial waste passes over these biomaterials, REs stick to the cell surfaces. The biomass is then harvested, and the REs are desorbed, removed, using a chemical rinse, e.g., acidic or chelating agents. Example organisms. Brown algae like sargassum are particularly effective because of their alginate-rich cell walls. Fungal biomass, e.g., Aspergillus, Rhizopus, is also used. Bioaccumulation. This is an active process where living microorganisms absorb and store REs inside their cells through metabolic activity. How it works? Microbes are exposed to RE-containing water or waste. Through specific transport mechanisms, the cells take up metal ions from the environment. The REs accumulate inside the microbial cells, sometimes bound to proteins or stored in vacuoles. Cells are later harvested and chemically or thermally processed to recover the REs. Example organisms. Certain bacteria such as Methylobacterium extorquens were genetically modified E. coli strains. Some cyanobacteria and extremophiles adapted to high metal environments. Biomineralization, emerging area. In some cases, microbes can precipitate REs into solid minerals as a result of metabolic reactions, such as changing the pH or secreting enzymes that induce crystallization. Potential output. Biogenic RE phosphate or RE oxalate compounds that can be filtered and refined. Advantages of bio-based RE extraction. Environmentally friendly, low chemical usage and minimal waste. Selective binding. Some microbes can preferentially bind REs over competing metals. Low energy. Operates under mild temperatures and ambient pressures. Scalable and decentralized. Can be applied at small scale, e.g., remote mining waste cleanup, or industrial scale. Challenges and limitations. Low extraction rates from dilute sources like seawater, unless concentrated through pretreatment. Complex purification. Biosorbed metals still need refining for tech applications. Biomass regeneration. The biosorbent materials often need to be regenerated or replaced. Stability and longevity. Living systems can be sensitive to toxins, pH, or salinity. Research and innovations. Genetic engineering is being used to design microbes with enhanced metal-binding capabilities or membrane transporters specific to REs. Biofilms and immobilized biomass reactors are being developed for continuous flow systems. Synthetic biology is exploring designer peptides and proteins that mimic biological metal binding for industrial use. Applications to seawater. Seawater contains rare earths in very low concentrations, 0.1 parts per trillion, so bio-based extraction from raw seawater is still in early research. However, it becomes more feasible when combined with concentrated brine streams from desalination, applied to undersea hydrothermal vents or sediments, where REs are more concentrated, used in marine mining wastewater recovery and recycling loops. What are the energy devices and green technologies that can be made from seawater or minerals extracted from seawater? Seawater and the minerals extracted from it play a crucial role in the development of various green technologies and energy devices that contribute to the transition to renewable energy, electric mobility, and energy-efficient manufacturing. By leveraging the abundance of minerals in seawater, we can produce materials essential for clean energy solutions, such as solar panels, batteries, wind turbines, and more. Here's a comprehensive overview of energy devices and green technologies that can be made from seawater or minerals extracted from seawater. Energy devices and green technologies from seawater minerals. Solar photovoltaic PV panels. Heat seawater-derived minerals. Magnesium, used in lightweight alloys for the frame and structure of solar panels. Boron, acts as a dopant in silicon, enhancing the performance of solar cells. Silicon, although not directly extracted from seawater, silicon is processed using byproducts from seawater desalination or minerals. How it works? Magnesium allows for the construction of lightweight frames that reduce the cost and energy needed for transport and installation. Boron is essential for creating efficient photovoltaic cells, while seawater-based processing can provide cleaner alternatives to traditional mining of these minerals. Lithium-ion batteries, used in EVs, solar storage, and grid backup. Heat seawater-derived minerals. Lithium, used in the production of lithium-ion batteries for energy storage in electric vehicles, EVs, solar panels, and grid systems. Nickel and cobalt. These minerals are critical in the construction of high-density cathodes for batteries, increasing energy capacity and longevity. Magnesium, emerging as a potential material for magnesium-based batteries in future energy storage systems. How it works? Lithium extracted from seawater can be used in batteries that store energy generated by solar panels and wind turbines, supporting the transition to clean energy. The development of more sustainable extraction techniques from seawater can help meet the rising demand for batteries without further stressing terrestrial mineral reserves. Wind turbines. Heat seawater-derived minerals. Rare earth elements, REs neodymium, dysprosium, and praseodymium are essential for permanent magnets in wind turbine generators. Magnesium, used in the manufacturing of lightweight structural components. How it works? Wind turbines rely on powerful permanent magnets made from rare earth elements, which are crucial for generating electricity efficiently. The extraction of REs from seawater can help secure a sustainable and geographically diverse supply of these materials for wind energy. Electric vehicles, EVs. Heat seawater-derived minerals. Lithium, used in lithium-ion batteries for electric vehicles. Cobalt and nickel, important for the performance of battery cathodes in EV batteries. Magnesium, used in lightweight alloys for vehicle frames and parts to improve energy efficiency. How it works? EVs rely on batteries powered by minerals extracted from seawater, such as lithium and cobalt, as well as lightweight alloys made from magnesium to reduce vehicle weight and increase range. Green hydrogen and synthetic fuels. Heat seawater-derived minerals. Chlorine and sodium, produced as byproducts from seawater electrolysis, which can be used in the production of green hydrogen. Magnesium and calcium could play roles in carbon capture and storage, CCS, or mineralization processes to synthesize green fuels. How it works? Green hydrogen is produced by electrolyzing seawater to separate hydrogen and oxygen. This hydrogen can be stored and used as a clean fuel for industries, transportation, and power generation. The development of efficient electrolysis technologies that utilize seawater could significantly reduce the cost of hydrogen production. Energy-efficient electronics and smart grids. Heat seawater-derived minerals. Gallium and indium, essential for the manufacture of semiconductors, high-efficiency solar cells, and LEDs. Boron, used as a dopant in semiconductors to improve electronic performance. How it works? Seawater can be a source of valuable metals like gallium and indium, which are crucial for the manufacture of energy-efficient electronics such as LEDs and transistors used in solar inverters, as well as smart grid technologies for efficient power distribution. Nuclear energy, seawater uranium extraction. Heat seawater-derived minerals. Uranium, present in seawater in trace amounts, and can be extracted for nuclear power generation. How it works? Seawater contains small quantities of uranium, which can be extracted through advanced technologies such as adsorbent materials designed to capture uranium. This uranium can be used as a fuel for nuclear reactors, providing a long-term, low-carbon energy source. Extracting uranium from seawater is considered a potential solution to the challenges posed by limited terrestrial uranium resources. Desalination and water purification. Key seawater-derived minerals. Magnesium and calcium, often found in seawater, and can be used in various water purification processes, including desalination and water softening. How it works. Desalination technologies, such as reverse osmosis and electrodialysis, can use seawater as a source for producing fresh water. The minerals extracted during the desalination process can be repurposed for other green technologies, contributing to a circular economy. Carbon capture and storage, CCS. Key seawater-derived minerals. Magnesium and calcium carbonates, used in mineral carbonation processes to capture CO2 from the atmosphere and convert it into stable mineral forms. How it works. Magnesium and calcium carbonates extracted from seawater can be used in carbon capture technologies that trap CO2 and turn it into stable, solid minerals, providing a solution for mitigating climate change. This process involves combining CO2 with minerals to create carbonates that can be stored safely. Why seawater? Seawater is a rich and sustainable source of various minerals essential for green technologies, and its use has several advantages. Abundant and renewable. Seawater covers over 70% of the Earth's surface and contains vast quantities of minerals, including rare earth elements and critical metals. Low environmental impact. Extracting minerals from seawater can be more environmentally friendly than traditional mining, which often involves significant environmental degradation and pollution. Geopolitical stability. Seawater-based extraction can diversify the supply of critical materials, reducing reliance on limited land-based resources controlled by a few countries. Future potential. With ongoing research and technological advancements, bio-based extraction methods, e.g., using algae, bacteria, or fungi, and renewable power desalination could make the extraction of valuable minerals from seawater more economically viable and sustainable. These technologies could play a key role in ensuring the materials needed for green energy systems are available in the future while minimizing the environmental footprint. Seawater, which covers over 70% of Earth's surface, is a rich source of a variety of minerals that are essential for producing clean energy technologies and energy storage systems. As the world transitions to renewable energy and sustainable practices, extracting minerals from seawater offers a promising solution to meet the increasing demand for materials used in technologies like solar panels, wind turbines, batteries, and more. This process involves the extraction of specific minerals from seawater, which can then be used to manufacture energy devices and green technologies. Below is a comprehensive explanation of the energy devices and green technologies that can be made from seawater or minerals extracted from seawater. Solar photovoltaic PV panels. Solar panels, which are crucial for harnessing solar energy, rely on certain minerals that can be sourced from seawater. Magnesium is used in the construction of lightweight frames for solar panels, making them easier and more cost-effective to transport and install. Boron, which is extracted from seawater, acts as a dopant in silicon wafers to improve the efficiency of solar cells. While silicon itself is not directly extracted from seawater, the processing of silicon can benefit from the byproducts of seawater desalination, thus integrating seawater-derived materials into solar technology. Lithium-ion batteries. Lithium-ion batteries are key to energy storage, especially for electric vehicles, EVs, and solar power systems. Lithium, a vital component in these batteries, can be extracted from seawater, where it exists in trace amounts. Additionally, minerals like cobalt and nickel, also used in lithium-ion batteries, are sometimes derived from seawater or sea-based resources. These batteries are central to the functioning of renewable energy systems, as they store excess energy produced by solar panels and wind turbines. By tapping into seawater to extract these materials, we can reduce the environmental impact associated with traditional mining. Wind turbines. Wind turbines, which convert wind energy into electricity, rely on powerful magnets made from rare earth elements, REs, like neodymium, dysprosium, and praseodymium. These REs are critical for the performance of wind turbine generators, as they make the magnets that help generate electricity from wind. While these elements are primarily mined on land, some research is focused on extracting them from seawater, where they are present in low concentrations. Magnesium is also used in the structural components of wind turbines to make them lighter, more efficient, and easier to transport. Electric vehicles, EVs. Electric vehicles are a major component of the transition to clean energy, reducing carbon emissions from traditional gasoline-powered cars. The production of EVs relies heavily on lithium, cobalt, and nickel for the batteries, which can be sourced from seawater. Additionally, magnesium is used in lightweight alloys for vehicle frames and parts, improving energy efficiency by reducing the weight of the vehicle. By extracting these minerals from seawater, we can ensure a sustainable supply for EV production without overexploiting terrestrial resources. Green hydrogen and synthetic fuels. Green hydrogen, produced through electrolysis of water, is a clean fuel that can be used in various sectors such as transportation, industry, and power generation. Chlorine and sodium, produced as byproducts of seawater electrolysis, are key components in this process. The extraction of hydrogen from seawater offers a sustainable alternative to conventional fossil fuels, with potential for large-scale production using renewable energy. Furthermore, magnesium and calcium could play roles in capturing and storing carbon, which could be used in producing synthetic fuels, thereby enabling the creation of carbon-neutral energy sources. Energy-efficient electronics and smart grids. Seawater is also a source of critical materials used in high-efficiency electronics, such as gallium and indium, which are used in semiconductors and LEDs. These materials are essential for developing energy-efficient devices like solar inverters and lighting systems, as well as smart grids that optimize electricity distribution. Boron, another element that can be derived from seawater, is used in semiconductors to enhance the performance of electronic devices. These materials support the development of energy-efficient technologies that are essential for the functioning of modern, sustainable energy systems. Nuclear energy. Nuclear energy provides a large-scale, low-carbon energy source, and seawater offers a potential solution to the limited supply of uranium for nuclear reactors. Uranium, found in trace amounts in seawater, can be extracted using specialized adsorbents. While the concentration of uranium in seawater is low, it is virtually unlimited, offering a potential long-term solution for nuclear power generation. If effectively extracted, seawater-derived uranium could help sustain nuclear energy production for the future. Desalination and water purification. Desalination technologies, which convert seawater into freshwater, rely on processes like reverse osmosis and electrodialysis. Seawater contains valuable minerals such as magnesium and calcium, which can be extracted and used in water purification and softening processes. Desalinated water can support agricultural, industrial, and residential needs, while the minerals extracted can be repurposed for use in other green technologies. This creates a circular economy where the byproducts of desalination can be used in renewable energy systems. Carbon capture and storage, CCS. Carbon capture and storage technologies aim to mitigate climate change by capturing CO2 emissions and storing them in stable, long-term forms. Magnesium and calcium carbonates, which are abundant in seawater, are key materials in mineral carbonation, a process that reacts CO2 with minerals to form stable carbonates. This process can be used to permanently store CO2, thus helping reduce the amount of greenhouse gases in the atmosphere. The use of seawater-derived minerals in CCS technologies is an important step toward achieving carbon neutrality. Seawater is a vast renewable resource that contains many minerals essential for the production of clean energy technologies. By extracting and utilizing these minerals, we can reduce our reliance on terrestrial mining, minimize environmental degradation, and ensure a sustainable supply of materials for green technologies. As research advances, bio-based methods for extracting rare earth elements and other minerals from seawater could further increase the efficiency and sustainability of this process. These technologies are essential for the global transition to a low-carbon economy, supporting the development of renewable energy systems, electric vehicles, energy storage, and much more.